Hi, I'm Frank Burridge. I am the project architect for the Woodley Year 10 Regenerative Futures Studio from McEldowie Partners Architects, and this is Lockie.
I'm Lockie, and I've helped design and develop this building system.
And so what we're doing here today, we're here for our fortnightly inspection of progress and quality and just answering any questions that the builder has. Yeah, look, the biggest challenge over the last few weeks was we originally wanted to use the site cut, soil from the site cut on the roofs. You can see when you come up here that there's the building to level the ground, which is much better for learning to have good flow through the spaces. We needed to cut back into the slope. It's much better for bringing light in as well. And we wanted to use the soil for the roofs, and we thought it was feasible based on the soil tests. What we found through making prototypes for this green roof was actually that the soil has a high loose clay content as well as sand content. And what happens when it gets really, really wet is that it seizes up and stops accepting water. And what that would have done is create surface water moving over the roof of the building and going out over the facade if there was a heavy rainfall event. It potentially would have exceeded some operational load limits on the roof, but it would have led to a bit of staining on the facade and things. So in the end, we've imported fill from nature's soil to use on the roof. It's not a bad outcome actually, because the soil from the site cut can be used for other landscaping works in the school, and we know that the soil that we're importing is going to be really, really good for growing all the native species that's going to support butterflies and butterfly habitat and bird biodiversity and connect in well to the reserve next door.
I mean, an obvious one, this Victorian winter, there's been a few little delays with the weather, but that's expected. But the other elements of the build are completed, and the builders are, trucking forward,
The weather's a good point, and I'm going to say it loudly, the waterproofers have been doing an awesome job keeping things going despite the bad weather. And we're standing at the moment in the green roof, and it's flood tested, so the waterproofing team have put on, there's a steel frame which you can see around us and you will have seen in former videos, and then on top of that there's a Durapanel substrate, which is the straw board, which pops down, and then there's a liquid applied tanking membrane and then a butanol membrane that goes out over the top that's welded. And the roof is designed to hold 35 mil of water, and then these cupolex domes get spread out over the top of the roof. So usually these are used for slabs, and that's what we use it for here. They get spread out in a grid over the roof and then covered with soil. So you end up with a cavity that allows for the free flow of water underneath, and then the soil comes in through the legs of these domes and makes contact with the water, and you can see there's actually really good contact there. And what that means is if there's a period of no rainfall, so a drought or a few months over summer where there's not much rain, the soil will wick up the water that's stored in here, and the plants will still be able to access water. And it means we can grow all kinds of species that otherwise would die off in the summer or in droughts. So it makes the building more resilient. It means that the habitat that we're putting up here for butterflies will be more relevant and operational year round. Sam Cox and his helper Louis have put together this amazing planting schedule for the roof of native plants that flower at different times of the year. So there's always a flowering plant on the roof. There's always a flower on the roof, which is great for native butterflies. So you can see the reserve that we're right next to over there has a lot of native plants and has native butterflies. The problem with those plants on the ground is rabbits, which eat the buds of the flowers and eat fresh shoots. Whereas up here, you can't get rabbits. So we can grow a whole bunch of plant species that support butterfly biodiversity that you can't grow on the ground. So this is actually adding something new to the reserve offering of the school, which is really, really exciting.
Definitely. And I think there's another element with the pods as well in this building system is it actually helps take some of the weight out of the actual amount of soil, so we can have, we're still allowed to have a good deep amount of soil for deep and growing, but these allow to take some of the weight out whilst allowing the water to flow really easily. So next time we're up here, you'll probably see some soil.
Yeah, you can see all the bulk bags of soil just out
ready to go.
Coming over here, we can have a look at how does the roof actually drain. Well, it's got these it's got really four drainage options. So it's got these two spouts here, and one of the spouts has got holes in the side which are measured at 35 mil above the membrane. So that's the primary outflow. So as it rains, the water levels out because it can free flow on the surface, and then it will just drain slowly out of that drain at 35 mil. Then if for some reason or another this drain gets blocked, which probably won't happen, but you've got to consider backups when you're designing a roof like this, there's a secondary overflow which goes down and then out the base of the facade. Now, if in the extremely unlikely event that both of those get blocked, there's a third overflow which goes straight out the facade. And then if in the extremely unlikely event that all three of those options get blocked and it's not draining, then the water will just flow out over the facade. And the structure is designed to be able to take that load. There'll be more deflection in the trusses if that happens, so we'll be able to tell that it's happening and fix the problem, but it'll never really get to that. The primary outflow goes to the Civic stormwater system, but what this roof system actually does, because it's holding 35 mil of water across the whole surface area, is that it means in a rainfall event, usually we build all of our buildings with hard roofs that are pitched. And that means that we're getting the water off the building as quickly as possible. That also means that we're getting it into the Civic stormwater system as quickly as possible. And the more and more hard surfaces that we build, the more and more pressure we put on the Civic stormwater system. And that's when you start to see flooding on roads, and you start to see pipes that are, spitting out water back up onto properties or onto the roads. So by having this green roof designed the way it is, when there's a big rainfall event, the water actually slowly seeps through the soil, and then it's held in this chamber, and then as it's seeping through the soil, it's slowly dripping into the downpipe. So if every roof was built like this, then it would mitigate stormwater flooding in urban areas.